Welcome to This Explainer. Today, we're diving straight into the hidden microscopic building blocks of our universe. We're going to look past what our eyes can actually see and uncover the invisible mechanics that make up literally everything you interact with every single day. Let's get right to it. So, take a second and really ask yourself, what is everything around us actually made of? Think about the solid objects you touch, right? Like a rock or even the screen you're looking at right now. Think about the liquids you drink, a glass of water, maybe some juice. And what about the completely invisible gases, like the air you're breathing into your lungs this very second? What's the one thing tying all of these drastically different things together? Well, the answer lies in the fundamental rule of our whole investigation today, the particle theory of matter. This is the scientific principle stating that all matter, literally everything that takes up space and has mass, is made up of tiny, constantly moving particles, like atoms and molecules. That's the big secret. Even when an object looks completely, perfectly still to us, on a microscopic level, it is buzzing with invisible activity.
Now, the behavior of these particles shifts drastically depending on whether we're talking about solids, liquids, or gases. In a solid, particles are packed tightly together. Since they're so cramped, their movement is super limited. They mostly just vibrate right there in place. In a liquid, they're still close, but they're loosely packed enough to actually slide and move past one another. And in a gas, total freedom. They spread way out, moving rapidly and randomly in every single direction.
Moving to Section 1, the mystery of flow. Why exactly do liquids spill while rocks sit perfectly still? When we compare solids directly to liquids and gases, the mechanics of flow become crystal clear. We know how particles are arranged, but how does that actually explain why a glass of milk will easily spill all over your table while a heavy rock just sits there holding its shape? Well, in a solid, because those particles are vibrating but locked firmly in place, the object stays rigid. A rock is going to stay shaped like a rock unless you apply some serious force to break it. But because the particles in liquids and gases are completely free to move and slide past one another, they flow. This microscopic freedom is the exact reason water easily pours into a glass to take its shape, and why air naturally flows out of a fan to fill up a room. But wait, if these particles are invisible, how can we possibly prove they're real? Let's jump into Section 2, the evidence, proving the invisible exists. We can actually prove this by just looking at simple everyday stuff. Clue number 1. Inflating a basketball. When you pump air into a deflated ball, it expands, it becomes firm. Why? Because you are actively forcing gas particles into that confined volume. And those particles, they don't just sit in a sad little clump at the bottom. No, they spread out rapidly. They fly around, pushing against the inside walls of the ball to fill up that empty space. You're literally watching invisible particles exert physical force. Clue number 2 takes this a step further, compressing air in a syringe. Imagine holding a regular medical syringe, covering the tip with your finger, and pushing the plunger down. It pushes in a bit, right? But then it gets harder and harder to press. This proves that gas isn't just one solid block. There's actually a massive amount of empty space between those gas particles. By pressing the plunger, you're physically forcing those particles closer and closer together, which increases the pressure pushing right back against your finger. Okay, our third clue moves us from gases over to liquids, dissolving sugar in water. When you stir some sugar into a glass of water, it seemingly vanishes, right? It's like a magic trick. But taste the water and you know for sure it's still there. The particle theory explains this perfectly. The solid sugar breaks down into its individual particles, and because liquid particles are loosely packed, the sugar particles simply slip right into the empty spaces between the water particles, hiding there completely seamlessly. And here's our final clue for this section. Evaporating salt water. Say you leave a shallow dish of salt water out in the warm sun. Eventually, that dish dries out, but a crust of solid salt is left behind. This perfectly separates two different types of particles. The liquid water particles gain energy, they turn into a gas, and completely escape into the air. Meanwhile, the heavier, stationary solid salt particles are left exactly where they were. All of this brings us to one of the absolutely most fascinating proofs of particle movement, a concept called diffusion. Diffusion is the process where particles spread out evenly throughout a substance without being stirred, without being mixed, or pushed by us at all. This is the ultimate unassisted proof that particles are continuously in motion on their very own. To really lock this concept in, think about diffusion in a liquid first. If you drop just a single drop of food coloring into a clear cup of completely still water and just watch it, that color will eventually spread to every single corner of the cup on its own. The water particles are constantly bumping into the food coloring particles, scattering them around. Now compare that to diffusion in a gas. If someone sprays a bottle of perfume in the corner of a large room, eventually you're going to smell it on the complete opposite side of the room. The scent particles are traveling freely right through the air. So whether it's dye in a cup or a scent reaching your nose, particles are always naturally on the move. Which leads us to Section 3, Transformations, Changing States of Matter. So, we know matter can exist as a solid, a liquid, or a gas. But how does it switch from one identity to another? The trigger for all of this is temperature. Here are the specific pathways matter takes to transform. Melting is the shift from a solid to a liquid. Think of an ice cube left out on the counter. Freezing is the exact reverse, liquid to solid, like putting an ice tray in your freezer. Evaporation is liquid to gas, which we saw earlier with that disappearing puddle of salt water. Condensation is the shift from a gas back to a liquid. You've definitely seen this when water droplets suddenly form on the outside of a cold glass of juice. And finally, sublimation. This one's a bit more rare, where a solid turns directly into a gas, totally bypassing the liquid phase entirely. Now, the absolutely crucial point to take away from this entire explainer is exactly what's happening to the particles during these transformations. It all comes down to energy. When you add heat, you are giving those particles energy. They start to move much faster, they aggressively spread apart, and their bonds loosen. That's why ice melts into water and water boils into steam. Conversely, removing heat takes away that energy. The particles slow down, they pack tightly together, and eventually they lock firmly into place, which is why water freezes back into solid ice. Heat equals speed and distance, while cold equals slow, tightly packed particles. We have covered incredible ground today, from vibrating solid particles to the free-flying gases that fill up our rooms. I want to leave you with a challenge before we wrap up this explainer. Where are you going to spot the invisible mechanics of diffusion or condensation in your own home today? Is it going to be the smell of dinner cooking spreading through the house, or maybe the steam forming on your bathroom mirror? The particle theory of matter is constantly in motion, all around you. Thanks so much for joining me, and keep observing the invisible world.